In section 7, we're going to be talking about factoring special cases. Now, the nice thing about this is, much like the special cases that we talked about with multiplying, where we talked about squaring the binomials, like these things up here, is if we remember the pattern, great. It's a shortcut. It might save a little time. If we don't remember the pattern, we just do things the way we've always been doing it. So when we look at these perfect square trinomials that they're called, okay, so down here we've got these perfect square trinomials in the middle. When I factor those, notice that both factors end up being the same. So here in the middle I've got a plus b and a plus b. Whenever I have the same factor twice, we combine those and we simplify that by writing it as a squared. Right? So if you look at the example here with x squared plus 8x plus 16, you notice that 16 is a perfect square. And both factors end up being 4s. So instead of leaving x plus 4 times x plus 4, we combine those and we put it in a simpler form and write it as x plus 4 squared. So anytime you have the same factor twice, you combine them and write it as a squared term. And the second example, notice not only do we have a perfect square at the back with 9, but that the leading coefficient of 4 is also a perfect square. Okay? So anytime I see perfect squares at the front and the middle, I need to be aware that I might have this pattern for a perfect square trinomial. And if I take a 2 out of the middle term, instead of having 12, I would have 2 times 6. Okay? Well, 6 is also the same thing as 2 times 3. 2 happens to be the square root of 4, and the 3 happens to be the square root of 9. So that's showing that you've got that AB, that 2AB pattern in the middle. But again, if you recognize it, great. If not, you just go about factoring these things the same way that we've been working on them. So we'll look at a few examples here. The factored form of x squared minus 12x plus 36. If I think of this in terms of the same thing that we've been doing, I'm thinking of what values are going to multiply to 36, but they're going to add up to negative 12. Well, that would be x minus 6 times x minus 6. But since both factors are the same, we simplify it by combining and writing it as x minus 6 squared, indicating that this initial trinomial is actually a perfect square trinomial. How about example 2? X squared plus 6x plus 9. Well, if I happen to notice that 9 is a perfect square, or if I think of it in terms of our other factoring, 9 is 3 times 3, so I end up with x plus 3 times x plus 3, which is really x plus 3 squared. Okay? So anytime we're coming up with our two factors being identical, we want to combine them and write them as one factor that is squared. Example 3, I've got a 49. So what multiplies to 49 but adds up to negative 14 would be negative 7 and negative 7, which means I have x minus 7 squared as my factor. So again, if I recognize the pattern, I can go right from here to here. If I don't, I just factor it the way that we've always done, and then combine those two factors into one squared term. So take a minute and read the word problem. So the question is asking us, what is the length of one side of the pixel? Well, what we know here is that these pixels are squares. Okay? And they're giving us the area of the pixel. So to figure out what one side is, I need to use the formula that the area is the length of one side squared. So what I really need to do here is I really need to factor this 4x squared plus 20x plus 25. Okay? So if I look at the patterns, I see that 25 is a perfect square. Its square root would be 5. 4 is a perfect square. Its square root would be 2. Okay? So I've got a perfect square at the front and the back, and 20 would be 2 times 2 times 5. Okay? So I do have a perfect square trinomial that would factor to 2x plus 5 squared. If I don't recognize that pattern, then I go right back to my previous factoring and I take a times c and I get 100. And what multiplies to 100 but adds up to 20? Well, that's going to be 10 and 10. So I'm going to rewrite my 20 as 10x and 10x. And then I'm going to factor by grouping. I can factor out a 2x, which leaves 2x plus 5. The second group, I can factor out a 5, which leaves 2x plus 5. So I have 2x plus 5 times 2x plus 5, which is 2x plus 5 squared. So you can see that if I recognize the pattern, I can get to the answer fairly quickly. If I don't, I just go about my normal factoring routine and I still get to the same solution. So I don't have to know the patterns. Again, they're just shortcuts. Okay, here's one factoring a difference of 2 squares. This is one that we really want to be able to recognize. Okay? Anytime I have a perfect square minus another perfect square, it's going to factor to the sum and the difference of their square roots. Okay? So for example, x squared minus 64 factors to x plus 8 and x minus 8. Because what happens is the minus 8x and the plus 8x that we would get in the middle of our FOIL, they fall out. So we're left with no x term. All we have is the squared and the constant. Okay? So we're always looking, if there's just 2 terms and it is a subtraction, are both of those terms perfect squares? So if we look at z squared minus 9, well, z squared is obviously a perfect square, and 9 is a perfect square. So it's going to factor to z plus 3 and z minus 3, the sum and the difference of their square roots. And again, you can always check by multiplying it back together. Here's my z squared. I'd have minus 3z, then I'd have a plus 3z, and then a minus 9. Well, the 3z's are going to cancel out because they're opposites, leaving z squared minus 9, which is what we started with. Okay, so you can always check your factors by multiplying them back together. Okay, so let's look at these two. V squared minus 100. Well, 100 is a perfect square, so this would factor to v plus 10 and v minus 10. Example 7, s squared minus 16. 16 is a perfect square, so it factors to s plus 4 and s minus 4. And again, I can do a quick check. There's a minus 4s. That would give me a plus 4s, and those things would zero out, leaving just the squared and the constant. How about example 8? Well, we've got the x squared. We've got a coefficient in front of the x squared, but notice that 16, that's also a perfect square. So here my a value would be 4x, and my b is going to be 9, which is the square root of the 81. So when I factor it out, I'm going to have 4x plus 9 and a 4x minus 9. Okay? Because 4x, if I square it, gives me the 16x squared. And if I take the 9 and square it, that gives me the 81, which is my a squared minus b squared. So it still factors from that same pattern. Right? Now sometimes we might not have a difference of 2 squares to start, which is why we always need to look for a GCF. No matter what type of polynomial or what type of expression we have, we always want to look for a GCF first. So in example 9, I noticed that the 24 and the 6, they have a GCF of 6. And when I factor that out, I'm left with a 4g squared minus 1. Well, 4 is a perfect square, and 1 is a perfect square. So this is another difference of two squares pattern. So now the 4g squared minus 1 also factors to 2g plus 1 and 2g minus 1. The sum and the difference of the square roots of those two terms. Okay? So keep in mind that no matter what type of factoring you're doing, always look for a GCF first. If it's not there, then just jump right into your normal factoring routine. Okay? So we'll work on some more of these tomorrow in class. See you then.